Hey guys, in this video I wanted to talk a little bit about optimization. So I think the best way to talk about optimization is to kind of just jump into some of these problems. So we'll start with this first problem here, and I'll kind of highlight the steps that I go through when I solve an optimization problem. So the sum of a number and 3 times another number is 12. Their product is a maximum. Find the numbers and the max product. So what is this telling us? This is telling us we'll let the first number be x and the other number be y. So this is telling us that the sum of a number and 3 times another number is 12. And we know that their product is a maximum. So I'll define this function, say p for product, and this will be x times y. And we know that it's a maximum. So in general, for an optimization problem, we're given two functions. We're given a restraint function, or what we're given. In this example, it's this guy here, and we're given something that we need to optimize. So in this case, it tells us their product is a maximum, so we need to maximize the product. So I am going to put a diamond next to my restraint function and a star next to the function I want to optimize. So I know which is which going forward. So the first thing I want to do is I want to use the diamond equation to solve for one variable. So I have that x plus 3y equals 12. So I'll solve for x because it's easier. So subtracting y from both sides, I get that x is equal to 12 minus 3y. So now I have this new equation, and it tells me x in terms of y. So I can take this equation and plug it into the product. So now that gives me this, that p is actually equal to, well, p is equal to x times y. I'm plugging x in, I get that p is equal to 12 minus 3y times y. Now remember, p is what we're trying to maximize. So a function, for example, p, has a maximum or a minimum when its derivative is equal to 0. We know that from, calculus 1 knowledge. It's our function, either if it has a minimum, it looks like this, and its derivative is 0 at the maximum point, or if it has a minimum, its derivative is 0 at the minimum point. So we want to take the derivative of this p and set it equal to 0. So the derivative of p for our product is, what I'm going to do first actually is I'm going to carry this multiplication out to make things easier. So I'll distribute this y and get this, and now I will take the derivative. P prime is equal to 12 minus 6y, and I know that I want, move things up here, I want p prime equal to 0. And that's going to happen when I set whatever p is here equal to 0. So I need 12 minus 6y equal to 0. So that means I need negative 6y equal to minus 12, or y equals 2. Cool. So now I have y is equal to 2, and I need to solve for my other variable, which is x. So I can take this y equals 2, and I can plug it back in here to get x. So x is equal to 12 minus 3y. That's the same as saying x is equal to 12 minus 3 times 2. So x is equal to 12 minus 6. So x is also equal to 6. So we want to find the numbers. So we found our numbers, right? I'll write them here in blue. X equals 6 and y equals 6, and we want the max product. So our max product is our product when we plug in our maximum values here. It's going to be x times y, or in other words, 6 times 6. So our maximum product is 36. Okay, so let's take a look back at our steps here. So the first thing we did is identified our restraint and our optimization functions. I'll call it an optimization function, the function we want to optimize. The next thing we did is we used our restraint function to solve for one variable, or sorry, like this here. We used our diamond to solve for one of the variables. Then we took that and we plugged it into the function we're trying to optimize. We simplified a little bit, and then we took its derivative and set it equal to 0. Then we solved for the variable that we could and plugged it back into our equation here to get the other variable. Okay, so for this next problem, I went ahead and wrote out the steps. So the problem is a rectangular piece of land is bordered on one side by a river. The other 3 sides are to be enclosed by 300 feet of fencing. What is the maximum area that can be enclosed? So in this case, it's going to help us to draw a picture. So I'll draw a picture here. So we have a rectangular piece of land. Draw a rectangle here. And one side of it is bordered by a river. So because that side is being bordered by a river, oop, I don't know why that disappeared there. Because one side of it is being bordered by a river, we only need to fence 3 sides. So we know that our perimeter is going to equal 300 feet. And we want to maximize the area that's enclosed. So we want to know a max. Okay, so the first step that we need to do is identify our restraint and optimization functions. So for my restraint function, I'm given that my perimeter has to be 300 feet. So P equals 300. So what is perimeter in this case? Our perimeter in this case, if let's say we label one of these sides X and Y, well, this side will have the same, and we don't count this side because it's being bordered by a river, so we don't fence that. So my perimeter in this case is going to equal 2x plus y, and this is our given. And the function we're trying to maximize here is the area. And area we all know is equal to length times width, or in this case, x times y. So we need to use our diamond equation to solve for a variable next. So we have that 300 equals 2x plus y. I'm going to solve for y because it's easiest, so I'll subtract x from both sides and get y is equal to 300 minus 2x. Okay, my next step is to plug into the star equation and differentiate. So a equals x, and then y we just solved for is 300 minus 2x. So what I'm going to do next is I'm going to distribute that x to make differentiation a little bit easier. I have 300x minus 2x squared. Then I'm going to differentiate with respect to x, and I get 300 minus 4x here for my a prime. So my next step now is to set my derivative equal to 0 and solve. So setting a prime equal to 0 is the same as setting 300 minus 4x equal to 0. So this tells me that negative 4x is equal to minus 300, and then x will be equal to, ooh, what's 3 times 25? 75. Okay, this tells me that x is equal to 75. So I have one of my variables. Now I need to plug it in to the other variable. Now I need to plug it in to get the other variable. So I'll use this equation here because I already have x in terms of y, or sorry, y in terms of x. So using that equation, I get that y is equal to 300 minus 2 times x, which is 75. So y is going to equal 300 minus 150. So y equals 150. Okay. Now I need to compute my optimal value. So I'm asking for the maximum area that can be enclosed. So my maximum area is going to be x times y, where x and y are my maximum values. So area maximum is going to be 75 times 150. So my maximum area is going to be, let's see here, 11,250 square feet. And that finishes the problem. Okay, so we're going to work one more problem. And before I start this problem, I think I've kind of been underselling the importance of drawing a picture for these problems. So if you're given a situation for an optimization problem where it would really like, it's talking about like a fence, or we're talking about like a shape, and we're trying to optimize like a shape within another shape, or a fence, it's really beneficial for you to draw the picture just so you can get a sense of what's going on. And also so that you can better identify and create your optimization and restraint functions. So we're going to take a look at this problem next. A 384 square meter plot of land is to be enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the sides. Okay, so we're looking at a plot of land here, and it's divided into 2 equal parts by another fence parallel to one pair of the sides. So we're looking at a situation like this. We have a divider in the middle of our um, shape here, like that. So we want to know what dimensions of the outer rectangle will minimize the amount of fence used. Okay, so we're given here that this entire plot of land is has an area of 384 square meters. And we want to know what the perimeter that will, or sorry, yeah, what is the dimensions that will minimize the perimeter, right? So let's label our sides here. So let's call this long side here y, and so this guy will also be y here. And then this guy will be, we'll say x, and this guy will be x, and that guy will be x. So our perimeter here, so first let's identify our given. So our restraint function here is that area has to equal 384. And we also know that area is x times y. The in total closed area will be the rectangle, or sorry, the area of this entire rectangle, and that's going to be x times y. And now our optimization function, the thing that we want to optimize, is perimeter. So our perimeter is going to be given by how much fence there actually is. That's going to be 2y plus 3x. Okay, so now we're going to use our diamond equation to solve for one of the variables. So I'll pick y. I'll solve for y. So we know that xy is equal to 384. So this tells us that y is equal to 384 over x. Oops, not x. So now I want to take this guy and I want to plug him into my star equation and differentiate. So p is equal to 2y plus 3x, which means we just solve for y. So we have 2 times 384 over x plus 3x. And now I want to differentiate. So my p prime is going to equal 2 times negative 384 over x squared. The derivative of x, 1 over x is negative 1 over x squared, plus 3. Now, we want to set that equal to 0 in step 4. P prime equal to 0 if and only if we have I'll write it like this. Negative 2 times 384 over x plus 3 equals 0. So that means that 2 times 384 over x is going to equal 3. And this tells us that x is going to equal 2 times 384 over 3. Oop, I made a mistake. Okay, so this should actually be squared. This x should be squared here from here. I forgot to square those x's. So I actually have x squared is equal to 2 times 384 over 3. So this tells me that then really x is equal to plus or minus the square root of 2 times 384 over 3. And x can't be negative because we're talking about a length, so we take the positive square root, so x is just the square root of all of this mess. So if we go ahead and simplify that radical, we get x is equal to 16. So now I can take this value, x is equal to 16, and plug it in to get my y value using this equation here. So y is equal to 384 over 16. And that just so happens to be 24. So now we need to, so it says the question is asking what dimensions of the outer rectangle will minimize the amount of fence used. So recall that our dimension here is x. So x is equal to 16 and our height is going to be y equals 24. So our optimal dimensions are 16 by 24. And that is all the examples I have for you. And that's optimization.